and our all staff meetings, have sent me some information and discussed it, but I think it would be great to try and, get some of maybe be able to sponsor through one of the programs, an aux sponsored competition, which I think would be wonderful.
Okay, Nassau has an indoor pool down near Kema and Kema, Texas. They have an indoor pool, and the Mate ROV program has been run there before. And there's a Coast Guard auxiliary member who was a judge a few years ago for the program. So that's one possibility also.
Right. Okay. I have to go back in my notes to see if maybe that one was suggested outside of sea perch, but I was familiar with sea perch. Teaching in the school system. That's a kind of a go-to robotics, program that a lot of teachers, if they have the robotics team at their school, they sorry, my voice is just failing me this evening.
Okay, guys,
usually their go-to.
I'm going to start things up now. So watch your time. I'm going to go blank, but watch your time. You can start talking again. You can start talking at the top of the hour.
Yep, I've got 8:58 at 2100 Eastern. I'll start my introduction. Same as last time, Mike, I'll just give the brief introduction to tonight's Tech Talk, a compacted version of your biography, and then hand it over to you.
Am I centered?
Let me check here. I have to change my view option. Yes, perfect. That looks great. Good evening, everyone. I'm PJ O'Neill, serving as the branch chief for STEM training and youth programs. Welcome to this month's Tech Talk on unmanned underwater vehicles, submersibles, and unmanned systems. This is part 2 of our series with Michael Kappas. The Tech Talks are sponsored by the U.S. Coast Guard Auxiliary, and the Boy Scouts of America Sea Scout program. I'll be coordinating your questions after the presentation, but feel free to post your questions in chat throughout the webinar. Tech Talks are held on the 4th Tuesday of the month at 2100 Eastern, except for this month due to the upcoming Thanksgiving holiday. There is no Tech Talk next month in December, and we'll resume our Tech Talk schedule in 2023, so please stay tuned. As a reminder, these Tech Talks are recorded. Tonight's Tech Talk will be recorded and posted on the Sea Scout and AuxScout YouTube channels, and they make for excellent free training available to you and your ship or flotilla. Our subject matter expert is Michael Kappas. He served as an officer in the United States Marine Corps for over 5 years and has been a member of the U.S. Coast Guard Auxiliary since 2009. He participated in federal responses and deployed as an auxiliarist to the Deepwater Horizon oil spill, the Texas City Wise Bill, Galveston Bay, and Hurricane Harvey. Up until June 30, 2022, he was a member of the Civil Air Patrol, which is the U.S. Air Force Auxiliary, and served as Assistant Operations Officer in Central Texas of the Texas Wing in charge of drone instruction. And he was responsible for youth education on drones within the Texas Wing. And he's conducted indoor and outdoor traveling drone shows for the Texas Wing and demonstrated different drone technologies to cadets, which is youth and senior members. Mr. Kappas has his FAA remote pilot's license and is instructor for pilots for the Academy of Model Aeronautics, instructing specifically on drones. He's a member of the Multi-GP, the largest FPV drone racing organization in the world, and has participated in many FPV drone races. I'd like to hand it over to our subject matter expert, Michael Kappas.
Thank you. Welcome to part 2 of Unmanned Systems, Commonalities and Differences. Please do not undertake any of the activities mentioned in this class without a license, without the proper knowledge, and without professional adult supervision. Okay, during our first class, we talked about 3 wireless radio frequency data links. We talked about a radio control link for the pilot to control the drone. We talked about a video downlink to view the video from the drone. And we talked about a telemetry data link to get information back about the drone and its environment. And here are the antennas associated with those links. Here's a video transmitter antenna, a radio receiver antenna, a telemetry antenna, and now we're going to add a 4th wireless radio frequency data link, the GPS antenna. We're also going to plot these 4 data links on the electromagnetic spectrum. You can see right here in green, 2.4 gigahertz band, that's for the radio control link. The 5.8 gigahertz band is for the video transmission link. The 900 megahertz band is for the telemetry data link. And here's the range for the GPS data link. You may also notice out to the left, we have in red, the automated identification system, 330 megahertz to 300 megahertz. And that's for manned and unmanned surface vessels to broadcast their location to other vessels so they don't collide. And that's where that is on the electromagnetic spectrum. Okay, our last slide in our first class dealt with the microprocessor and the microcontroller, the brains of the unmanned systems. And let's go to a video on this subject.
For years, we've been running our Blue ROV2 with the Pixhawk Autopilot and Raspberry Pi computer. On the Pixhawk runs the ArduSub ROV control software, which is a branch of the larger ArduPilot project that we created and have managed since 2016. The Raspberry Pi computer, meanwhile, manages communication and video streaming through our open source companion software. The Navigator flight controller replaces the Pixhawk with modern, capable, consolidated hardware. It's a board that plugs into the Raspberry Pi computer's expansion port and transforms it into a fully featured flight controller. It's focused on marine robotics applications like the Blue ROV2, but not limited to just that. You can also use it to control drones, ground robots, or anything that moves, really.
Okay, so unmanned surface vehicles. Above water, they use radio waves for communication and imaging. Underwater, they use acoustic waves for communication and imaging. And in just a moment, we're going to see a video on unmanned surface vehicles. Okay, unmanned surface vehicles are more capable, flexible, cheaper than other vessels. They can vary in weight from tens of kilograms to thousands of kilograms, with speeds that can vary from 1 meter per second to 20 meters per second. Okay, USVs can be controlled remotely by a human operator and may also have autonomous functionality. Many USVs can alternate between full autonomy, semi-autonomy, or set to manual control. Here we see a USV. It is programmed to follow a route. Program the software to follow a route and use sonar scanning. Here's the imagery. And here's the data, telemetry data back from the drone in its environment. surface vessel is following its program to follow this route and conduct sonar scanning to produce imagery underwater. It's about 5 meters per second. That's an autonomous surface vessel. Power and propulsion. USVs can be powered using diesel, gasoline, hybrid electric, battery, and or renewable energy. There are conventional powered USVs and renewable powered USVs. And the image on the slide here is both. It is a dual powered USV, conventional and renewable. Let's talk about renewable powered USVs. Solar, marine grade flexible photovoltaic panels. The combination of solar cells and electric thrusters are used to power these vehicles. Here you can see solar power for electronics. Wind power. Wind passing over the wing produces thrust for propulsions. And you can see in this image here, it says wind power for propulsion on this 5 meter tall wave. And then there's wave power, and let's go to a video on the wave glider.
And information. The wave glider is designed to capture both. It's the world's most experienced ocean robot, propelled by wave and solar power. On the surface, the wave glider has everything needed for a self-contained data collection system. A powerful computing environment, scalable, flexible payloads, multiple communications options, solar panels and battery packs to power it all. The wave glider's innovation only begins at the surface. Below the surface is a sub attached by an umbilical cord that captures wave motion and transforms it into forward motion. As waves move the float up and down, wings on the sub rise and fall, propelling the vehicle forward. The slightest wave motion is enough. A solar electric thruster is available for extra speed when needed. Wave gliders can tow large payloads, hit speeds up to 3 knots, and be out at sea for many months at a time. Wave gliders have done some amazing things. They've crossed oceans, survived the toughest of conditions, gathered data from ocean depths to the surface, autonomously communicated with other assets, and even set a world record.
Okay, renewably powered unmanned surface vessels are unique. They're distinct from other unmanned systems. Okay, now let's talk about the components of an unmanned surface vessel. The radio controller, and here we have an image of a pilot grabbing a radio transmitter, moving the left throttle stick forward to speed up the engine or motor, and that gets the propellers moving, and which produces thrust, and off it goes, unmanned surface vessel. Okay, other components: receiver, battery, microprocessor, and or microcontroller, electronic speed controller. You may remember this from quadcopters. In this particular, ESC can be used in cars, ships, and underwater thrusters. Okay, one of the things electronic speed controller does is it converts a DC power from the battery to AC power for the motor. And here we have the electronic speed controller being plugged into the lithium polymer battery, and it's converting that DC power to AC power to this motor, which doesn't have any propellers on it. He's going to test it by pushing the throttle stick forward on the radio transmitter, and you can see it works. Okay, moving along. Other components include the rudder, the IMU, which includes a gyroscope, accelerometer, and compass, power distribution unit, GPS, sensors, and more. Here's another picture of the components, and you might notice that many of these components are the same as those on quadcopters. Others are unique. For example, cooling pump, cooling reservoir. The ESC or motor of an unmanned surface vessel or unmanned underwater vehicle may need water cooling so that they do not overheat. This may consist of tubes running through the ESC that keep it cool, or a cooling pump, reservoir, or fan. Okay, aerial drones have air circulating through the components, so they don't use cooling
Power
pumps.
being delivered with these high voltage systems. So something to consider when you're picking out your ESC. Now next, you want to make sure you get an ESC that has water cooling. This has water pickups and it has tubes running through the ESC that keeps it cool, opposed to an ESC that has a built-in fan. Water pickups with water cooling. That's to help your brushless system run much cooler and efficient. Now we're going to get into the motor choices. You want to choose a motor that's going to fit your boat.
Okay, water cooling for maritime drones. And here is the schematics of an unmanned surface vessel, or how the components work together. Okay, USVs can have space-based sensors, surface-based sensors, and subsea sensors. A USV may have several sensors for imaging and aquatic observation. For example, FLIR, forward-looking infrared. It detects thermal heat and creates an image, but cannot see through water. And in this image, you can see the thermal signature of a person in the water, but there's no thermal signature underwater because FLIR does not work underwater. Okay, LiDAR, light detection and ranging, a scanner, sensors. It measures the distance to one target point by illuminating it and analyzing the reflected light. LiDAR targets an object on the surface with a laser and measures the time for the reflected light to return to the receiver. The three main components of a LiDAR instrument include scanner, laser, and GPS receiver. Here we see an unmanned surface vessel doing some LiDAR scanning, taking imaging with the LiDAR camera on the mast. And here's the actual image. Here's the LiDAR imaging. This is what it looks like. LiDAR pulses out, LiDAR returns the form of this image. Okay, USV sensors for navigation. A USV may have several sensors for navigation. Obstacle avoidance is important due to the variability and diversity of the marine environment. Now, you may think those are a lot of sensors. How can I handle all that information? Well, you're not alone. The vehicle also has a challenge handling all the information from all these sensors. That's why it has a built-in algorithm that will fuse this data into a best estimate of orientation in a three-dimensional space. It's sensor fusion, a software for sensor fusion of all these sensors. And it's often called a Kalman filter. That's often the name. Okay, let's talk about software on unmanned surface vehicles. Here's a video from Europe that deals with software and navigation sensors and aquatic observation sensors.
Water velocity. So, how does it work? It all starts with planning a monitoring and treatment mission. The Dronic system is supplied including software and a base station. With these tools, a user can indicate the lake and its contours, upload other data, and hence determine the path in the lake that the Dronic master will monitor once it's deployed. After the mission is set, a user-friendly and robust master USV is released in the water. This innovative robotic system is equipped with a variety of sensors to allow it to navigate through the lake independently and to locate the blue-green algae hotspots. Among others, it's equipped with echo sounders for underwater obstacle avoidance and 3 range sensors for above-water obstacle avoidance. The system communicates with the base station real-time through a long-range Wi-Fi connection, which makes it possible to interact with the mission at any given time. A camera on board the system allows real-time supervision from the shore. Through GPS, the Dronic can position itself in the lake and upload water quality data along with its location. The robotic boat can operate and navigate in 2 modes. Either it follows a predefined track or it navigates in an adaptive way based on real-time analysis of the recorded sensor measurements. The former mode is used to cover and map the entire area of interest. The latter mode can be used to search for a maximum value of a specific parameter. The boat is battery powered and its economic engine design allows it to operate for 8 consecutive hours, since the correct control of the vehicle's actuators is essential for optimal manoeuvrability of the Dronic. Embedded software and sensors for measuring algal concentrations enables the master USV to track down algal hotspots and autonomously change course or send the slave USV to the hotspot based on these findings. In addition, software for obstacle avoidance makes sure that the equipment is safe to operate, even when the lake is in use recreationally. The master USV is used to analyze the water quality and to detect, localize and map algal blooms. Essential parameters are monitored, such as photosynthetic pigments, chlorophyll A, psychocyanin, turbidity, temperature and depth level. The monitored data is transferred to the web-based software. Once the master USV has found an algal bloom, a second drone is launched to neutralize the threat using ultrasound waves, providing a direct and localized treatment.
Okay, there's other software. We should be familiar now with ArduPilot project used with quadcopters. Let's take a look at ArduPilot Mission Planner used with unmanned surface vessels. Here we have a route programmed in ArduPilot Mission Planner with all these waypoints, C1, 2, 3, 4, 5, 6, all the way up to 20, 22, 23, etc. And here we have the unmanned surface vessel following that route that it's been programmed to follow in the Mission Planner software. Same thing with Q ground control. Again, this is familiar from quadcopters. Here we have a route this unmanned surface vessel is following. It's been programmed in the software. Waypoints 1, 2, 3, 4, and there's home.
The halfway point.
You see this Q for Q ground
Make a
control
turn.
software.
Just made the halfway point turn.
Okay, and there's other software. Okay, but let's talk about types of unmanned surface vessels. Unmanned surface vessels come in all shapes and kind, including water rescue robots, robotic buoys, and more. This water rescue robot is called Emily. That's the name. Use a handheld radio transmitter to control the vehicle, control the robot. You'll see that handheld radio transmitter at the end of this video in the bottom right-hand corner. Water rescue robot. See the handheld radio transmission in the bottom right transmitter? Okay. But lo and behold, this very same water rescue robot, they've learned to program it with software and artificial intelligence.
Time to getting out to that person. So you want the computers to get better, the algorithms to start learning the patterns.
They're testing out a new user interface, navigating using thermal sensors to locate people in the water, and fine-tuning a system that automatically slows the robot down as it approaches its target.
You want that robot boat not to just blindly zoom over there and run the victim down, but now use artificial intelligence to slow down.
They're customizing these new programs for large-scale water rescues.
Okay, notice on some of these boats, there's a radio transmitter. So you can use radio transmitter to manually control the unmanned surface vessel, or you can use software. Let's look at a robotic buoy. Robotic buoy. And here's some images placing the robotic buoy in the water. And here's the software on the right here, where they're getting data back, telemetry back from the robotic buoy. Okay, let's move right along. We'll talk about model radio control boats for recreation, for sporting.
All right, finally, Traxxas Spartan, the boat. I get to run it today. Here is my two cell LiPo packs. I could run 6S in this, but I'm not going to because I haven't driven it before, so I don't want to go crazy on my first run. Look at 12,800 mAh on this 2S LiPo from Jen's Ace. That's going to give me, I'm going to have to guess, around 7 or 8 minutes. We'll see. Radio's on. Everything's pretty much stock except for some aluminum upgrades I've done to the back. I'll show you what I mean. Just want to get this going. Nice. So I'm mid-upgrade. I've got a balanced prop on there. I've got the RC Boat Bits aluminum upgrades on here. This is a rudder with dual cooling, but I don't have it installed yet for the motor in there. That's exactly why I'm running the 4S as well.
Okay,
as,
now let's see this
but
boat
maybe long running
launched.
power. Who knows? Here goes the test.
Looking at a radio transmitter, handheld radio transmitter to launch it to get the engine going and the propellers moving. Okay, there are two model sporting associations.
Half
North
throttle.
American Model Boating Association and the International Model Power Boat Association for sport recreation activities. Note, the components on electrical powered model boats are often similar to those on unmanned surface vessels, but gas and nitromethane powered model boats often have very different components. None of these model boats uses a flight or microcontroller. They do, however, have many of the same components as a quadcopter, as you can see from this image. Okay, now we're going to talk about unmanned underwater vehicles. These vehicles can be remotely operated vehicles controlled by a remote operator, or autonomous underwater vehicles operating independently from direct human input.
Here are two unmanned ocean explorers. Can you spot the difference? An AUV, or autonomous underwater vehicle, explores ocean depths without any attached cables. Researchers drop an AUV in the ocean and pick it up at a pre-selected position. An ROV, or remotely operated vehicle, is also unmanned, but is connected to a ship by cables. A person on the ship drives it around. ROVs are often used in situations where diving by humans is either impractical or dangerous, such as working in deep water or investigating submerged hazards. ROVs and AUVs carry equipment like video cameras, lights, and robotic arms to grab samples for study. By going where humans can't go, these underwater robots help us safely study the ocean.
Okay, unmanned underwater vehicles often operate in a harsh environment under high ocean current, heavy hydraulic pressure, and poor lighting. And let's look at the schematics. I've got orange arrows pointing to the microprocessor and the microcontroller of the unmanned underwater vehicle. Okay, let's talk about thrusters. Okay, autonomous underwater vehicles can rely on a number of propulsion techniques, but propeller-based thrusters are the most common by far. These thrusters are powered by electric motor, which is powered by batteries. One of the components of this is the electronic speed controller.
The T200 is a three-phase brushless motor, which means that unlike a lot of motors, you can't just connect it to power and expect it to spin. It needs an electronic speed controller to work. Today we're going to be doing that with the basic ESC right here, which is an electronic speed controller for any sensorless brushless motor, but we're going to be using it on the T200. The basic ESC here has a couple wires coming off of it. It's got a red and black wire, that's for power input to the speed controller, and then it's got three wires over here that connect to each of the three phases of the thruster. You can see there's matching colored wires on the thruster. And then last, we've got this small cable here with a little connector. This is the PWM input signal that's actually going to control the speed of that thruster.
Okay, the electronic speed controller interprets the control command sent from the flight controller to the motors. It tells the motors what to do. Video transmission systems on unmanned underwater vehicles. Underwater real-time video transmission is challenging due to frequent dependent signal attenuation, ambient noise, multipath distortion, propagation delay, and the Doppler effect. High data rates are required to relay video. Unfortunately, underwater communication has low data rates and very limited transmission bandwidth because it uses acoustic waves instead of electromagnetic waves. AUVs are wireless and cannot transmit live video images. A tether is essential if you want to view live video previews from the depths. ROVs, however, that's ROVs, remotely operated vehicles, can send 4K video feeds in real time to the operator on the surface because it has a data tether and or an umbilical cable that can reliably transfer data such as images and videos in multi-wire tin copper wire. Note, waterproof and pressure sealed camera housings are used for camera and video components underwater. Okay, let's talk about sensors for imaging and aquatic observation on unmanned underwater vehicles. Forward-looking infrared cannot see through glass or water. Traditional thermal imaging doesn't reach below the surface of the water. Sonar. Sonar is long-distance acoustic communication. The speed of the sound waves allows sonar to be extremely useful for seafloor imaging. But because of the noise and interference sound waves produce, there are risks to marine life. In addition, background noise and other errant sound waves often interfere with the accuracy of the data. Sonar is still the most viable choice. Let's look at light and optical imaging. Light and optical imaging has limited range, and it's more accurate in clear water. Okay, now let's talk about the sensors for navigation in unmanned underwater vehicles. You can use, some of the sensors include a depth gauge, a compass, a camera, and an inertial navigation system. You can also use sonar for unmanned underwater vehicle navigation. Sonar can be used in the following ways: as an echo sounder to measure the vertical distance between the vehicle and the hard bottom, as a sector scanning sonar to scan for objects horizontally around the vehicle, and it can also be used for acoustic positioning. Let's take a refresher on what acoustic positioning is.
Latin long readout. Now, GPS radio signals don't pass through water, so we have to use this special system called USBL, basically a set of sonar beacons that allow for the triangulation of the ROV, and a GPS chip at the controller lets the system correlate data and create an active Latin long of the position of the ROV. Now,
okay, now let's look at these video of the acoustic positioning systems that can be used for navigation of the underwater vehicle. Okay. Underneath the boat, they've got a transducer. A transducer sends out sonar signals in the form of sound waves and receives return echoes. Okay, you're going to see this right here in the form of binary data. And on the ROV, it has a beacon, a transponder, which receives acoustic signals and transmits a unique return signal. You notice there's also a diver and an autonomous underwater vehicle that are also getting in on the action there. Okay, now we're going to look at side scan sonars. They come in two forms. The first is towed by this surface vessel. There's a cable underneath this surface vessel towing a side scan sonar, which is conducting sonar imaging underwater to produce an image, which you're going to see on your screen here in the upper right-hand corner. See the image underwater? That's a side scan sonar. It's being towed by the surface vessel. And here's another example of a side scan sonar, but this time it's embedded in an autonomous underwater vehicle. These are all acoustic positioning systems. Lastly, there's multi-beam imaging sonar. And this is on a remotely operated vehicle. You'll notice this remotely operated vehicle has the cable connecting it to the surface. Through that cable comes power from the surface and instructions from the pilot. And back to the pilot from the ROV are the data that the underwater vehicle collects, including the video images and the sonar imagery. This is multi-beam sonar scanning. And as this ROV scans with sonar, you'll see the image in the upper right-hand corner. And watch as these fish come into view off to the right, bottom right. As these fish come into view, you'll also see them in the sonar imagery in the upper right-hand corner. That's multi-beam imaging sonar. All right, inertial navigation systems can be improved with a Doppler velocity log, a device similar to sonar, which measures the rate of travel over the seafloor. Let's talk about software on unmanned underwater vehicles. Again, ArduPilot, the ArduPilot project, a familiar term from quadcopters and unmanned surface vehicles. And here's an image of ArduPilot Mission Planner. See where this arrow is pointing at sonar range, sonar voltage. So you're seeing some of the same software. Q ground control, the background on this slide has Q ground control software. You can see right there. Oh, let me just mention that ArduSub is the sub project under ArduPilot for underwater projects. Okay, moving right along. Unmanned underwater vehicles use waterproofing and pressure proofing of components. Okay, that's why you need water cooling, because they're encased so they can heat up, so which results in the components sometimes heating up, so they need to be water cooled. Okay, now we're going to talk specifically about one type of unmanned underwater vehicle, the remotely operated vehicle. ROVs can vary in size, ranging from a shoebox to a large van, depending on the type of mission it needs to accomplish. ROVs operate in midwater or very near the bottom. There are four main types of ROVs: a work class ROV, a light work class ROV, an observation class ROV, and a micro or mini ROV. And let's take a look at a mini ROV that's used by the Coast Guard. This is a Deep Trekker DTG-3. All-in-one control system. Seamless sensor and sonar integrations. Simultaneous integration of sonar and USBL. ROV on moving map display, real-time route and log. That's getting that telemetry back. Okay, here are some components of the remotely operated vehicle. And let's look at an interesting video.
Hey guys, so I found these underwater thrusters with brushless motors, and I'm going to be using these to design my underwater drone, and I'm going to make the drone look kind of like a stingray. So I'm going to have two thrusters under the wing, and then I'm going to have a third thruster in the back to control the tilt of the drone, and then these two will control the steering. So I have them all hooked up to the ESCs here. And to use these, you're going to want to use electronic speed controller that is reversible, so you can reverse the direction of the thrust underwater. So I also wanted to kind of go over the direction of rotation. So if you look closely, these two propellers are actually mirrored images of each other. So depending on which way you look at this, to produce forward thrust, you have to rotate this propeller clockwise. And to produce forward thrust out of this one, you have to rotate the propeller counterclockwise. And the reason for this is the same reason in quadcopters that we spin the propellers in different directions. And this is because when you spin a motor, there's a reactionary force that is opposite to the direction of rotation. And this is how we control the yaw with the quadcopter as well. So for the underwater drone, if I had two motors that spun the same direction, it's going to want to drift. So you have the two motors spinning in opposite directions, it cancels out those reactionary forces. So this is the camera from the last video, and to get the live feed to the headset and the FPV monitor, I'm going to have an Ethernet cable that is attached to a flotation device, and then that's going to have the antenna for the FPV transmitter, as well as the antenna for the actual control of the ESCs as well. And that way, if I give it a 25-foot tether, I can basically have a tetherless experience where the drone can go out, you know, a mile and then dive 25 feet. If I put a 50-foot tether on it, it'll dive 50 feet. So, but I'm going to actually start with a 25-foot tether. To demonstrate the reactionary force, we can actually use this motor that's not connected to anything. So you can see it's rotating in the opposite direction that the propeller is spinning.
Okay, components of the ROV. Here's some more components, and let's look at another video describing components of an ROV in detail, comprehensively, more or less.
The Blue ROV-2 is a remotely operated underwater vehicle with a camera, lighting, and thrusters that allows you to explore, inspect, and study things underwater. For the purposes of this video, I'm going to assume that you already know what an ROV is, and I'll focus on the specific features of this ROV. Let's get into it. The ROV frame has 2 side panels, a bottom panel, and 4 center panels, creating a rectangular structure and providing places to mount the enclosures, the thrusters, the buoyancy, and the ballast. This design is inspired by work-class ROVs, which typically have a similar structure, allowing things to be easily added to the ROV for different missions. You can attach just about anything to this frame. At the top of the frame are these blue fairings, which hold polyurethane buoyancy foam, used to give the vehicle additional buoyancy. And on the bottom here are stainless steel ballast weights. They can be added, removed, or moved around to balance the vehicle and to maintain neutral buoyancy based on what you have installed. The buoyancy on the top and the ballast on the bottom makes this vehicle statically stable, meaning that when it sits in the water, it always wants to sit upright and stable so that you've got a solid camera view and a stable platform to hold any sensors or equipment that you're diving with. There are 6 thrusters in this standard configuration, and there are 8 thrusters in the heavy configuration over here. On the standard, there are 2 vertical thrusters on the top here in the middle, and on the heavy, there are 4 vertical thrusters. Those vertical thrusters help you go up and down. And then there are 4 thrusters on the bottom in what's called a vectored configuration, where each of these thrusters is at roughly a 45-degree angle. The thrusters themselves don't rotate, but by varying thrust on each thruster, you can create a thrust vector in any direction. That means you can drive the vehicle forwards, you can drive sideways, or you can drive at anywhere in between, like off to a 45-degree angle. This configuration is ideal for driving in real-world conditions where there's often currents coming from different angles, and you want to move the vehicle sideways as you inspect or view a surface. At the center of the ROV are 2 enclosures. These were both updated to our improved locking enclosure design in the R4 version of the ROV. On top is the electronics enclosure, and down here on the bottom is the battery enclosure. The electronics enclosure has a camera at the front with 1080p high resolution and sends a live, low latency stream up to the surface for the pilot view. Behind that are the rest of the electronics. Right here is the Navigator flight controller running Blue OS, which is also a new improvement on the R4 version of the ROV. The Navigator consists of a Raspberry Pi computer with an array of added sensors, inputs and outputs, and expansion capabilities. It uses its onboard sensors to determine the attitude and heading, and outputs to the thrusters to automatically stabilize and control the vehicle based on pilot inputs. The ROV runs on our Blue OS software, which encompasses a number of different elements and is open source and user modifiable for your application if necessary. Blue OS manages the operation of the vehicle, including that AuxScout control system software, the camera, the communications through the tether, and it has expansion features to support other sensors, sonars, and payloads. The Navigator connects to the Ethernet network that connects the vehicle to the surface and forwards the video stream and controlled data to the topside computer. It's connected to the Fathom X tether interface board, which transforms that Ethernet connection into a long-range connection over just 2 wires. And last, there are 6 speed controllers mounted at the back, connected to the thrusters and to power. On the outside of the enclosure, at the back, are cable penetrations leading to the thrusters and lights, as well as a pressure and temperature sensor, a pressure relief valve, and several blank penetrations for expansion. Below the electronics enclosure is the battery enclosure, which holds a battery during operation. The battery typically gives you about 3 to 4 hours of operation in normal conditions. Starting with the new R4 version of the ROV, you can choose either acrylic plastic or aluminum enclosures. The acrylic enclosures are rated to a depth of 100 meters, and the aluminum enclosure increases that to 300 meters. The tether on this vehicle runs from the vehicle to the surface. This particular ROV has a pretty short tether that can be managed by hand, but we have tether lengths up to 300 meters, and we have an optional tether spool to manage those longer lengths of cable. At the surface, this cable plugs into the Fathom X tether interface, or FXTI box, which has a connector for the tether and a USB connector to go to your laptop computer. Once you're connected and powered up, you connect to the vehicle using the Q ground control software. That one's also an open source software application, and it runs on Windows, Linux, or Mac, and provides live video stream, live data view, ability to adjust the parameters on the vehicle, and an interface to any gamepad or joystick controller to pilot the vehicle.
Okay, each vehicle can be different and so can have different or unique components. Unlike aerial drones, unmanned underwater vehicles use electronic speed controllers that are reversible so that you can reverse the direction of the thrust underwater. Okay, brushless direct current motor. This, together with the batteries, is the heart of the ROV. It is the element which gives the propellers the power to generate thrust. Thrusters generate propulsion for the ROV. Most work-class ROVs use a combination of electric and hydraulic power underwater. The frame of an ROV provides a structure to attach the thrusters, camera, lights, tether, and other components of the ROV. ROVs are often assembled using a box-shaped steel, aluminum, or plastic polyvinyl chloride frame.
This is a pretty neat little ROV. It was developed by the Office of Naval Research as part of their Sea Perch student competition. They hold this competition every year. It's a pretty neat design, made out of PVC pipe. It's got some flotation foam on it. It's got 3 motors housed in film canisters filled with wax to seal.
Okay, moving right along. The tether, the unmanned underwater vehicle can have a tether and or umbilical cable that connects the ROV to the surface. It can contain copper metal wires to supply electric power and or wires or optical fiber optic cables to transmit data back and forth to the surface. Let's talk about the radio transmitter. Surface controls can range from something that looks like the control room for a spaceship to something as simple as a smartphone. In any case, the surface controls provide a physical interface for the pilot to control the vehicle and a display of feedback from the vehicle, including the camera view. The radio controller connects to the ROV wirelessly or by tether. And here's an example of wireless connection by using a gateway Wi-Fi buoy to the drone, which is connected by this floating gateway Wi-Fi buoy by tether to the drone, or the radio controller can be connected directly by tether to the drone. Okay, let's talk about the ground control station. They come in different shapes and size, as you can see on this slide. You get the point of view of the camera on your ground control station screen. You get telemetry data back on the screen of the ground control station. Let's talk about movement of the ROV.
Now, vertical motion is achieved by using the up and down thruster, the thruster in the middle. I activate the thruster, shown here by the green propeller, and it pushes the ROV down. If I stop the thruster, it should float in water and not move up and down if it's somewhat neutrally buoyant. I reverse a thruster, shown here in red, and the system moves back upwards. Now I use the forward and reverse thrusters, the thruster on the left, for horizontal motion. I activate the motor, shown here with the green propeller, and it'll push the ROV forward. If I stop the motor, it'll stop in place. If I reverse the motor, shown here in red, the ROV will move backwards. Now let's take a look at how I turn the ROV. Now this is a top view looking down. In the middle you see the vertical up and down thruster. On the left hand side you see the 2 forward and reverse thrusters. Now to turn right, I fire up the thruster on the left, denoted by the green propellers, pushes water backwards to the left, and the ROV will turn to the right. Turn the thruster off and it'll stay in that position. Fire up the right-hand thruster, as denoted by the green propeller, and it turns the ROV to the left. Now, if I want to turn quickly, I put one thruster forward and one thruster in reverse. You see the directions here of the two propellers, and that makes the ROV turn quickly.
Okay, now let's talk about the second type of unmanned underwater vehicle, the autonomous underwater vehicle, or AUV. An autonomous underwater vehicle is a robot which travels underwater without requiring input from an operator. It can travel by drift, drive, or glide. Here's another definition of an AUV: an unmanned, untethered underwater vehicle that carries its own power source and relies on an onboard computer and built-in machine intelligence to execute a mission consisting of a series of pre-programmed instructions, potentially modifiable online by data or information gathered by the vehicle sensors. And here's the onboard computer, this red pointing arrow. Okay, characteristics of AUVs. This is a good educational video.
AUVs don't have to house human bodies. They can be smaller, more efficient, and can go deeper.
We can survey as much as 2.5 kilometers wide per AUV, so we can cover a lot of ground, and we can take sonar imagery down to 3 to 5 centimeters.
But the average ocean depth is over 10,000 feet. That means AUVs involved in bathymetry or search and recovery missions have to be incredibly tough.
The vehicle has to be designed to withstand tremendous pressures of the deep ocean. There's no light, so if you want to take a picture, you've got to bring your own illumination. The other challenge is communication.
The deep ocean is pitch black. There's no internet, no cell service, no GPS. And with ocean currents, AUVs aren't able to maintain fixed, predictable positions. Once you send an AUV on a mission, for all practical purposes, it goes dark.
Underwater communication is done acoustically with sound. The bandwidth is really low, so that the amount of information you can send through the water column is really, really small.
What you've got is like worse than the 90s dial-up internet by orders of magnitude. And you're trying to send really complex information about where they're located in a 3D space.
But new AUV technology aims to skirt this limit.
Okay, an AUV carries its own power supply and has no physical link to the surface.
Autonomous underwater vehicle. Loco is a visually guided underwater robot built from approximately $4,000 worth of components, largely off-the-shelf and 3D printed. The robot's hardware and software design is intentionally modular and as open as possible. With a depth rating of 100 meters, a maximum speed of 1.5 meters per second, and a typical battery life of 2.5 hours, Loco is an AUV designed to lower the barrier of entry into the world of underwater robotics research. The robot is equipped with a set of human interaction capabilities, including gesture recognition, diver following, and robot communication via motion.
Here are the components, an example of some of the components of an autonomous underwater vehicle. Here's some more components. AUVs have servos, just like quadcopters, servos that control rudders and fins. Just like fixed-wing aircraft have servos that control
when you water level
rudders, ailerons, and elevators.
You've got less to sub to push under really.
Okay.
That's the best way I can describe.
And okay, so that's, and then at the back you've got two servos.
Yeah, two
Here are the
servos.
servos on the right.
One controls your rudder, top and bottom. They're linked together inside the tail cone.
Yes.
So if I just turn that one for you, that's the servo there.
You can see the servo turning, that white part there connected to the black, and there's a second one right there.
And the back one really is the most important because
Right there.
it has an automatic leveler on the sub. So when I control the dive planes, the rears will automatically try and level the boat out.
And that's electronic.
It's all done electronically.
So it's like a.
It's autonomous.
Okay.
So yeah, just.
Is that a gyro effectively?
Yeah, basically, it's like helicopters. You know how they have gyros.
Yes.
But just the opposite for a sub.
Okay.
So.
Servo mechanism. Okay, here are the schematics for an autonomous underwater vehicle. Okay, power. While most AUVs use rechargeable lithium batteries, some of the larger AUVs use aluminum-based semi-fuel cells that are higher maintenance. The most common propulsion methods for AUVs are propeller-based thrusters and Cort nozzles, usually powered by electric motors. AUVs may also glide through the water. By changing buoyancy, underwater gliders are able to alter their depth and use airfoil wings to convert this movement into forward motion. And here we have a sample in yellow of an underwater glider, but let's take a look at another underwater glider in this video.
Underwater gliders, there are one type of autonomous underwater vehicles. They don't have propellers outside. They work based on change of buoyancy. For long endurance operation, they can go 6 months with one battery charge. They have two problems. They are slow and they are not very much maneuverable.
Okay, they're unique. Let's talk about movement and navigation on AUVs. Most AUVs use an inertial navigation system.
It has a Kalman filter in it. It has sensor fusion built into the device that gives you a much more accurate output. It's a very high quality device generally. So an INS is going to include a Kalman filter, which is going to consist of how the sensor itself fuses all of the individual parts into one and gives you a navigation output with everything incorporated. This often includes gyro, magnetometer, and accelerometer. And in an INS solution, it also includes GPS. So it'll take those things and give you a navigation output that your robot can then use to understand where it is in the world.
Okay, 5 types of forces influence the motion of an unmanned underwater vehicle: drag, weight, buoyancy, thrust, and lift. Does that sound familiar? Because except for buoyancy, those are the same forces that influence an aerial vehicle. Similarities: electronic wiring of components of unmanned systems. Soldering is the fusing together of 2 electrical components using a metal alloy called solder. Soldering is used for the electronic connections on unmanned aerial vehicles, unmanned surface vessels, and unmanned underwater vehicles. Warning: soldering is a potentially dangerous activity due to extreme heat of soldering device and the use of lead, which is toxic. Okay, let's compare Pixhawk flight controller and components for an unmanned aerial vehicle on the left to the Pixhawk flight controller and components for an unmanned underwater vehicle on the right. They look very similar. I count 8 components or connections that are either similar or identical between these 2 wiring diagrams. There are some differences, but clearly there are some similarities. Okay. And to close out this class, I'm going to leave you with a summary of the main similarities and differences amongst unmanned systems. And that finishes our class for today. Thank you for your attendance.
All right, well, thank you very much, Michael. Quick question. In your experience, whether you're trying to rebuild or refit, whether it's an aerial drone or underwater, have you run into any supply chain issues with getting parts, whether they be for transponders, the microcomputers, say like Raspberry Pi 3, or even with brushless motors? I know that some parts have been on back order, and just wondering if it's affected your or any teams that you've worked with ability to refit any of your vehicles.
Okay, good question. One of the amazing things about the times we live in is that much of the components and the equipment for these unmanned systems have become cheap and widely available. Really, it's growing industry. But you brought up another point, which is that there's a lot of demand now that more and more people are getting involved in this field. So you do occasionally have that problem where a whole bunch of people want the same thing. So a particular company could be out of stock, in which case you could look at another company or just wait. but you got those two things going on.
All right, one more quick question, unless any more pop up. With the different software interfaces, understanding there's a wide variety and it's going to depend on your specific vehicle. But say you bought a complete kit, are they often included with a proprietary software system for controlling the vehicle and obtaining the telemetric data, or do you basically have a choice to decide on which software systems you may use?
Okay, that's a great point. A lot of these, what I did in this class was teach you about the individual components, but when you get out there in the field working with these systems, you find that some of these components are connected in a proprietary system. In other words, they only work with other types of components and other types of software. So you do have to do your homework before you purchase an unmanned system to make sure that everything you're getting is compatible, because in some cases they will be exclusive to a particular system, but in other cases you'll have interoperability between components and software. So I would say you have to do your homework.
Okay, good advice. Well, I want to thank you very much for sharing your time and expertise with us again for this part two of the system. Again, for everyone that is tuning in tonight, the recording of the workshop will be posted on the CScout and AuxScout YouTube channels. So please encourage your shipmates to tune in, whether it's within your group at a meeting or getting together to review some of the material. And hopefully if you're not already interested in becoming a drone pilot or in submersibles, that you have a good starting point. All right, stay tuned for our next Tech Talk that will come up in January of 2023. And thank you again, Michael. Good night, everyone.
Good night. Thank you. Okay, I'll talk to you later. Thank you.
Yeah, Michael, thank you very much.
Have a good night.
All right, you too. Hey there, Peter.
Hello.
All right.